Okay, thank you very much. Does that sound okay? Great. So this is joint work with Nikolai, Kudasov, and Emily Riehl. I guess by now we've seen a lot of quite involved category in Niels's and Nima's talk, but just for reason of self-containment, or if you've missed the last two talks, some kind of down-to-earth motivation for this category theory business. So if we're looking at methods or functions in a program and we want to compose them, we should employ sufficient care. For instance, if you look at two kind of mathematical functions like this, you might ask, what happens if I want to compose them, if I want to do some computation and then plug it into some other computation. So there's instances where this makes sense. If you start off with an integer, you might end up with a rational number, and you can just continue in the realm of rational numbers with this second computation. But for instance, the first function here would make sense for matrices as well, but then you wouldn't be able to compose with the second function because it's not clear how you would define it on the level of matrices. Like it would not be clear right away how to make that type check. So we have to keep track, as a moral of this, we have to keep track of the domain and codomains of our functions. And category theory is really an excellent environment for this. So a category is a structure that consists of a bunch of objects and morphisms or arrows between them, such that we can compose them to yield a kind of a third arrow like this. And also we want to have these identity morphisms, and composition should obey the reasonable laws, namely associativity and unitality with respect to these identity morphisms. So categories are not only a way to organize composition, but also identifications or isomorphisms, as we've seen in Nima's talk in particular. So via invertibility of morphisms, we can define the notion of isomorphism in a category. And you might encounter a category such that all its morphisms are actually isomorphisms. That's what we call a groupoid. So there's also some kind of connection to groups as well. It's kind of a simultaneous generalization. Well, it's kind of a blend of these two notions in some way. And now zooming out a little bit, we might look at transformations between categories now. These are called functors. So a functor is kind of a map between categories that acts on objects, but it also acts on morphisms in a reasonable way. Namely, it should preserve composition, but it should also preserve identities. And then we might also look at transformations between morphisms or morphisms between morphisms. These are called natural transformations. And they're given by a bunch of morphisms in the target category, such that for every morphism F in the domain category, we get like an induced naturality square in that way. This in itself gives also rise to a notion of isomorphism between functors by requiring that these horizontal components here all be isomorphisms. We get the notion of natural isomorphism. Another perspective sort of related to the displayed categories that we've seen in the two talks before is that we can use functors to encode objects parameterized by some other category, some base category. For instance, we could look at families of sets indexed by a category. That's what some people call a presheaf. An example of such a functor is the Hom functor, where you fix an object A, and then you look at all the morphisms in that category starting from that object, the action on morphisms is given by post-composition. And now you might kind of view these representable or these Hom functors, you might view them as some kind of elements that you can use to probe your functor f, which might lead you to the question, what can we say about the morphisms or the natural transformations from these Hom functors into any given f? The nice statement to make is that, in fact, we can completely understand that object because it's just given by evaluating f at that A. This is known as the Yoneda lemma here in sort of the most basic, most classical form. And it's a fundamental principle in category theory. Given the connection to functional programming, you might have seen this before. When using Haskell, for instance. And it's really something that is used throughout any area of math that uses category theory in a meaningful way. So we've seen in particular in Nima's talk how categories themselves can sort of have different dimensions. The kind of dimensionality I'm now interested in when dealing with infinity categories is I don't want to just look at morphisms, I want to look at morphisms between morphisms. So like the universe of categories itself forms a higher dimensional category by looking at functors as the morphisms and natural transformations as the morphisms between the morphisms. And then you might even thinking about iterating this, so why stop at any given n? And this leads us to the notion of infinity category. So specifically, I'm interested in a version of infinity category where only the one morphisms have a chance to be non-invertible. So the picture for these higher dimensional morphisms should be something like what you see below. But I'm kind of assuming that these higher dimensional cells, these like thick arrows, will always be kind of bidirectional. But you still have to somehow take care of them because it's like explicit higher dimensional data to take care of. And there's a range of applications this has today. Developments in homotopy theory, which is like the theory of deformations in mathematics, has a lot to do with that, but also in computer science and concurrency theory or rewriting, we encounter these structures, or in mathematical physics. And in fact, this leads us to viewing a category as a kind of topological object itself, in a sense up to deformation from a geometrical point of view or identification propositional equality from a logical or type theoretic perspective. So in fact, homotopy type theory and univalent foundations have proven like a great framework to do a kind of synthetic version of homotopy theory and dealing with these higher dimensional structures, being able to organize them in a nice way, amenable to formalization. But somehow the development of actual infinity category theory has remained unsettled, to some extent at least. So there are different approaches, but the problem with arrows being not necessarily invertible, that's kind of a non-trivial challenge for type theoretic approaches. But there exist some approaches, and parts of them have been formalized, which is what I want to explain today. So an infinity category for us, it should be like a category, but composition of one morphisms is not given as an operation, but rather it's given as some kind of topological data. So we're requiring one morphisms to be composable up to a space of these composition data, a space which turns out to be contractible, so essentially to be equivalent to a point. but nonetheless, as a set, that the problem is that this still would involve some data and definitely some handling in terms of the higher dimensional data and their coherences. So how would we express something like this in homotopy type theory? The problem is that homotopy type theory can deal with path types, with identifications, but it's not clear how to deal with or how to even define directed arrow types. So there are some frameworks you could think about to deal with that. Our work takes place in Riehl Shulman's simplicial type theory. There is a whole story about the semantics that one can tell. Basically, there is a precise sense in which this synthetic notion corresponds to what in traditional set-theoretic, foundation-based higher category theory has been well understood and accepted as models for infinity categories. So all is well in regard of kind of homotopical soundness. The main result of the formalization that I want to introduce you to is a version of the Yoneda lemma in that setting. So in the synthetic setting, it reads as follows. Assume we have some base category A and some term little a. Then looking at a certain kind of type family with some good transformation properties, C, over that base. Evaluation at the identity gives us an equivalence between this pi type here and the fiber at our fixed elements A. And this is kind of a type theoretic translation from the version of the Yoneda lemma that we've seen before. But now it's actually in the context of not just one-dimensional categories, but infinite dimensional categories. So we formalized this in the RZK, or RESC proof assistant, developed by Nikolai, which you're free to try out yourself. So it's completely open source, and there's a VS Code plugin to kind of remind ourselves of the framework. At first, we start with basically Martin-Löf type theory. So we have sigma and pi types, where kind of geometrically, these help us to understand or to identify type families equivalently as projections from the sigma type, the dependent pair type, to the basis. And we're also able to talk about sections of that family, meaning dependent functions. And the power of Martin-Löf identity types gives us a way to talk about kind of paths in a type and then higher dimensional paths between that type again. Which kind of canonically gives rise to the structure of infinity groupoid on every type. So what will be important for the Yoneda lemma is to make sense of this good transformational behavior. So in Martin-Löf type theory, by the way that these identity types are defined, every type family kind of conveniently transforms according to the path that we have in the base. So given a path like this in the base gives us a path in the total space of this family between the fibers, which you can also view as a kind of lifting operation of this path. And eventually we would like in the type theory to first of all deal with directed arrows, and then we also would like to be able to lift these directed arrows in the same way as we've done for these paths. So how can we actually achieve this kind of structure? How can we import this or create this in our type theory? That's what the simplicial extension of HOT due to Riehl Shulman is about. So first of all, what they do is they add a bunch of strict shapes, simplicial shapes. So first we start with a directed interval called delta 1. We take all the powers of this, giving us, well, the degenerate case where we just have a point. It would also give us a square and then a cube and a hypercube and so on. But we also want to be able to carve out simplicial shapes or subshapes of those out of these cubes. So in particular, we can cut out the standard n simplices, like the 2 simplex, which is this filled triangle here. But we could also just look at the boundary, or we could look at just the sort of generic pair of composable arrows, which is denoted with this lambda right here. And that's something one can kind of conveniently express in a separate layer of that standard. In a separate layer added to the standard kind of type theory. And now to kind of connect these layers in a meaningful way, they add a gadget to the whole story called extension type, which is also, if you've seen cubical type theory before, it's also something you find there. So the idea is we want to capture, given a partial section of a family, we want to capture all the strict extensions of that given partial section. And the strictness is important here because it precisely allows us to do things as strictly as possible so as not to get a headache while still maintaining sort of the good homotopical properties of the construction and not breaking homotopy invariance or equivalence invariance. So basically you can imagine these extension types to be a kind of pi type but with strict side conditions. So given a family P over a big shape psi, if we have a section A on the smaller shape, we now add this kind of bracketed pi type consisting exactly of terms, sections, like total sections of the family that strictly or judgmentally restrict to the partial section A. The Hom type we obtain by instantiating the big shape with delta 1, which is the free directed arrow or the generic directed arrow, and then just imposing on the endpoint, on the starting point and the endpoint, the values that we want the morphism to connect with each other. And the nice thing is that just by the way that the new type formers are set up, we can just work with the family from the get-go, and so we obtain a dependent version of the Hom type. So just as in the picture before, we had a kind of an arrow in the base, like a path in the base, and then kind of a path lying over that path. We can play the same game right here by looking at an arrow W in the base and a dependent arrow H lying over it in a strict sense. And we can also do this for higher shapes because our shape theory is kind of sufficiently rich, so we can look at 2 cells like this and similar or more complicated things. So now we want to finally be able to talk about categories in that setting. So a pre-infinity category or Siegel type is a type that should have weak composition in the sense mentioned in the beginning. So if we have a pair of composable 1 arrows, we want to be able to compose them in a unique way up to homotopy. And we can kind of conveniently impose this condition by saying that, well, for our type A, for it to have composition should mean that it should perceive any 2-cell, any composite triangle, or it should perceive any pair of composable arrows exactly as a simplicial 2-cell, so as a filled 2 simplex in a natural way. This is what the condition here means. Now, to get an actual infinity category out of it, we have to impose the rest completeness or univalence condition that Nima also talked about in some guys in the previous talk, where, well, with the directed Hom types that we have now, we could also sort of define what should be an isomorphism by requiring some invertibility condition. And a priori, it's not connected to the sort of primitive path types in a strong way, but we can make them coincide by also imposing a condition. And we can talk about infinity groupoids or discrete types merely by saying that any directed arrow should be invertible or should be a path. So we get this kind of zoo of canonical higher categorical structures in our theory. From a syntactic point of view, and as I kind of briefly mentioned earlier, you can make this precise semantically and really show that it gives you the well-established correct concepts. So the syntax matches with the intended semantics. So why even work in that system? So it turns out that just from this definition, you get a lot of the expected behavior. Like you don't even have to impose. I mean, first of all, note that now being a category is actually a proposition for some reason. The reason for this is that, okay, our types are something kind of inherently geometrical. We can probe it by all kinds of shapes. And then some of these shapes, for some types, some of these shapes kind of collapse in some intricate way. And then we might call that type a category. Like that's roughly the story that's going on. And we can actually, just from requiring this composition up to homotopy operation, or condition more like, we can prove associativity. Again, not in a strict sense. So this equality sign here really means propositional rather than judgmental equality in the sense of Martin-Lev type theory, and likewise for unitality. Any map between types that happen to be Siegel will automatically preserve composition and identity, so it will be automatically a functor. And there is a nice theory of natural transformations also, where the naturality kind of just follows from being a morphism in like in a functor or a function type. So finally, we want to talk about type families that transform covariantly with with arrows in the base. So any type family transforms both co and contravariantly with respect to paths. What about if we replaced the path with a directed morphism? So if we have a morphism from A to B in the base, we want to have some kind of function from the fiber at A to the fiber of B. So this is true for a variety of type families. So the first in that setting also being proposed and investigated by Riehl Shulman, which is the one that I'm focusing on today, that we've formalized the Yoneda lemma for in my own work. Some of it joined with Ulrich Buchholz. We've also considered more general notions, also two-sided notions, currently not formalized, but in principle that should all be possible in this proof assistant. So a covariant family should be a family such that given any arrow u and any point on the left-hand side in the total space, we can uniquely lift the arrow u to an arrow lying over it. That's the condition. And it turns out that this sort of is very well behaved. So now I'm assuming to work over a base that is actually Siegel, actually a category. Then every fiber will turn out to be discrete. So we have something like a synthetic homotopical, a synthetic version of infinity categorical presheaves or covariant presheaves in that case. We actually do get a lifting operation from this contractibility condition. And it also behaves natural in the sense that if we're given two covariant families together with a fiber-wise map, the fiber-wise map will commute with the lifting operations of the two families. So for instance, just as in the initial example for one category is the covariant Hom family is a covariant family in that sense. And now the sort of full statement of the Yoneda lemma reads as follows. Let's assume we're over Siegel type A and we fix a term little a, as well as a covariant family C over A. Then evaluation at the identity gives us an equivalence like this. So if you unravel this, we're looking at a kind of uniform dependent family of fiber-wise maps from Hom A blank to C right here. And of course, the canonical thing to do with that is, okay, just to look at endomorphisms of A, evaluate it at the identity, which would give us an element in C of A. So that's a well-typed map. And we're claiming that this is an equivalence, and actually it's natural in both the element A and the family C. So the kind of remarkable thing, or the non-trivial work, is to define, first of all, a map into the other direction. This we can do now using transport. And now we have to show that actually this defines an equivalence, so it's like inverse to this F-it map. So in the one categorical case, if you're defining this family, you actually have to, if you're defining this map, actually some work goes into showing, oh, it actually lands in that type, which is like some type of natural transformations. But here it's completely for free, just from this kind of extra uniformity you get out of working in the synthetic setting. And then proving, so the one direction of this equivalence is it's kind of easy if you know that lifting or transporting along an identity also gives you back an identity. And then the other direction is a bit more involved, but it also just follows from naturality properties and covariance of the Hom family. So the point I'm making is that working in this setting, and you can see this kind of nicely in the formalization, gives you an easier proof of a much stronger statement. So in summary, what we've contributed is, first of all, or I should say what Nikolai, with some students of his, has contributed is a new proof assistant RZK. Then with our team, together with Frederick Böcke, have contributed an initial formalization of standard results from HOT, as well as some synthetic infinity category theory, including the Yoneda lemma, which is what our contributed paper is about. And then in the meantime, some bigger group of people has joined us and significantly expanded and improved this theory. This library. I should also mention that, alluding to the comparison to the one categorical Yoneda lemma, our project, the article as well as the repo, contains a lean formalization by Sina Hazratpour, of which you can find some comparative discussion in our paper. So you're very happy to join us if you're interested. We have a Zulip chat linked right here. Here are some references where I specifically want to highlight Emily's AMS Notices overview article, kind of about the philosophy of this synthetic infinity category theory. And with that, I'll thank you very much for your attention.
Thank you very much. Do you have any questions?
Hi, I'm kind of curious about knowing what kind of things this RZK proof assistant gives you to above working in, say, like cubical AGDA or book HOT with univalence axiom in some of the more traditional proof assistants.
Just happens to be in some sense, it happens to be the first implementation of this specific type theory. So there are some kind of analogous developments by, for instance, Stanley Carter and Matt Weaver in a kind of cubical version using these kind of Siegel types. So the advantage to really working with that theory of ours or of Emily and Mike's is that there you really do know that what you're doing semantically corresponds to the correct homotopical notion, which is not clear in the cubical case. Like that's one answer. And also, if you compare it with kind of the story of univalent categories that Nima told us about, what we're doing is really a synthetic notion. So it's like being a category is a property in our theory. It's not a structure. And that also has like semantic implications as well if you're comparing it with kind of univalent categories or something like that.
I see. Thank you.
Hi, so my question is about this naturality in C. So in particular, originally this Yoneda lemma, this infinity categorical analog, was proven in HTT, and there's this. The statement is slightly different from yours, but I imagine maybe it's equivalent or something like this, where they have a Yoneda embedding, and then they have this a property of this thing that they also have naturality in C, right? Like if you have a functor in C from C to D, then there is an induced map in the other direction, and by some kind of adjoint functor theorem, that thing is a right adjoint, so you get a one in the other direction as well, and then that square commutes. Now, in one category theory, this is it's a fairly easy thing to prove, but in infinity category theory, as far as I recall, this is a somewhat technical proof. So I wonder if this trouble shows up anywhere in your approach, and if so, how does it manifest?
So now are you talking about naturality in the base?
Naturality in your category.
In your category, yes. So in the base, like what I called A, right?
Yes.
Yes. So yeah, I can't give an answer to this right now, but it's a good question to think about. I mean, one thing to say is that this version of the Yoneda lemma, you can think of it as like a fibered Yoneda lemma, which might also, I'm not sure right now in like HTT exactly what version is used there, but so this is definitely a version where you don't need to talk about the infinity category of whatever spaces or something, but of course you could also think about a version where this would come up.
But do you get something like a Yoneda embedding? Is that a consequence of your statement?
You see it somehow, but you see it in a different way. It's not reified in that theory, because we don't, like, I haven't talked about the infinity category of spaces at all, for instance. So it's so by that we also can't talk right away about like actual pre-sheaf infinity categories in that setting, but it's it's something we're thinking about too.
Okay.
Yeah.
Thank you.
Yeah.
More question?
Hi. So if I understand correctly about these infinity one categories, they can be strictified to have a composition operation which is strictly associative and unital or something like that. And since you are going to have this strict shape in your theory, is there a reason you don't want to go the extra mile and actually have these categories being strictified?
Yeah, because we want to do infinity category theory, like proper infinity category theory.
But isn't like categories enriched in spaces proper infinity categories?
But there, I guess you're assuming like set theory as on the meta level or some kind of extensional theory. But we're working in an intentional theory.
Thank you.
Quickly.
I mean, just to add a comment, I don't have a question. Like, even in just like normal set theory, like you cannot really use strictly simplicial enriched categories to do like infinity category theory, because like they're like even just forming like over categories, so like simple constructions don't really work in this setting, and that's why like for example HTT, which was mentioned, uses quasi categories. This is in some sense like a formalization using complete Siegel spaces. Like even in like very strict setting of like classical math, you really want non-strict notions of infinity categories to be able to like reduce like, I don't know, adjoint functor theorem, blah, 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 whatever you want to do. And yeah, so that, it doesn't matter in that sense. Like you can strictify one, but you don't want to have a strictified theory.
Okay, well, thank you again. And thank you to all the speakers for their lovely talks. That's the end of the session. And I guess CP returns after lunch.